Hello everyone. In last class, that is in previous session, we were discussed about problems on a short transmission line. So now, in continuation of the next concept is medium transmission lines. So in short transmission line calculations, the effects of the line capacitance are neglected, as I told, because such lines have smaller lengths in case of short transmission line, and transmit power at relatively low voltages, as I told, that will be less than or equal to 20 kilovolts, that is 20 kV. So however, as the length and voltage of the line increases, the capacitance gradually becomes of greater importance. I'll repeat, if the length and voltage of line increases, the capacitance gradually becomes of greater importance. Since medium transmission lines have sufficient length, as we discussed earlier, that will be having the length of 50 to 150 kilometer, so that also the voltage capacity is in between 20 kilovolts, that is more than 120 kilovolts, sorry, that will be more than 20 kilovolts, so that the effects of capacitance cannot be neglected in case of medium transmission line. Therefore, in order to obtain reasonable accuracy in the medium transmission line calculations, the line capacitance must be taken into the consideration. So the capacitance is uniformly distributed over entire line, that is the entire length of the line. So here the localizing the line capacitances given reasonably accurate results. The most commonly used methods for the medium transmission lines, that is known as localized capacitance method, for the solution of medium transmission line as end condenser method. The first method is end condenser method, second method is nominal T method, and third method is nominal pi method. So let us discuss about end condenser method. So in this method, the capacitance of line is lumped or concentrated at the receiving end, that is near to the receiving end or near to the load end, as shown in the circuit now. So here, so this the capacitance which is connected near to the load side or near to the receiving end side. The load side is nothing but receiving end side. So this method of localizing the line capacitance at the load end overestimates the effects of capacitance, as you are seeing the circuit diagram now. So here one phase of three-phase transmission line. This is having one phase of three-phase transmission line. We are writing this circuit diagram as also will be representing this is equivalent circuit diagram in terms of single phase by converting that three phase to single phase. As I told, if the circuit is balanced, then only we can convert three phase equivalent circuit diagram into a single phase equivalent circuit diagram. So all the values should be line to line values here. So look at here, let IR is nothing but receiving end current, or else you can say it as the alternative name is load current per phase. Similarly, R is resistance per phase, as I told, will be representing three phase into single phase, that is three phase to single phase. We'll be writing representing the equivalent circuit from three phase to single phase, so that R is nothing but here resistance per phase. Similarly, XL is inductive reactance per phase, C is capacitance per phase, and we'll be having the IR is having the angle between IR and VR is phi R is nothing but cos phi R is the power factor at the receiving end, also power factor of the load. So this load which is the current which flows to the load IR, which is depending on type of load, either it is inductive load or capacitive load or else resistive load. So that, as I told here, let Vs is sending end voltage, Vr is receiving end voltage, IR is load current per phase, or else you can say it as receiving end current, XL is inductive reactance per phase, C is capacitance per phase, cos phi r is receiving end power factor. So let us see the now phasor diagram. So here what we are doing, the phasor diagram will be taking a receiving end voltage. Here voltage is a reference, that is receiving end voltage VR as a reference. So we'll be assuming load is inductive load, so that IS or else IR. Okay. So if we'll be considering the load as inductive load, I is lags the voltage at an angle of phi. If we'll be considering the capacitive load, I is leading the voltage. So now we just look at the circuit diagram, taking the receiving end voltage VR as a reference phasor, so that we can write VR as VR plus J0 in terms of rectangular form, whereas the load current IR is I into cos phi r minus j sin phi r, as we discussed in short transmission line. So now look at the phasor diagram. VR is a reference, so that IR lags VR at an angle of phi r. IR lags VR at an angle of phi r. Similarly, if you want to get Vs, you can write Vs as VR plus Is into R plus Is into XL. Look at the diagram now. So before drawing the phasor diagram, you have to understand the circuit diagram. So Vs, you can write here it as Vs is given by Is into R plus Is into XL plus VR. VR. So that you have tried Vs. Before writing the Vs, what we are doing, we'll be taking VR as a reference. So for the VR as a reference load, by considering the load is inductive load, so that IR lags VR. Considering the load is inductive, so that IR lags VR at an angle of phi r. So the first step is IR lags VR by taking VR as a reference. Once you take this, then you have to write Vs is given by VR plus Is into R into Is into XL. VR we know. If you want to write Is into XL, so that draw a line which is parallel to the line Is. So now we'll be having doubt that how can you write Is. So Is is nothing but sending end current. So this is also lags Vs. So this is also lags Vr, but the value of Is, the magnitude of Is is less than the magnitude of receiving end current. That is a load current. The sending end current is less than the load receiving end current. So that draw a line which is parallel to Is, then draw a line which is perpendicular from the tip of Is. You can get Is into XL, so that we add VR Is into XL plus Is into Is into R plus Is into XL, you can get Vs. So now the angle between Is and Vs is phi s, that is the receiving end voltage. So the next is to write IC, that is a capacitance current. So capacitance per phase current. So how can you write this capacitance per phase current? So it is given by, just look at here, VR is a reference, as I told. VR you can write as VR plus J0. So IR, as we discussed in a short transmission line, IR into cos phi r minus J sin phi r. By taking VR as a reference, IR lags VR at an angle of phi r. Capacitive current, how can you write the capacitive current? See here, VR divided by minus JXC, minus JXC. So here VR divided by minus jx. Why it is minus? Because it is in fourth quadrant. So VR minus jx you can get, sorry, VR divided by minus jx. So here minus j, it becomes plus when it will be writing 1 over j is nothing but plus j. 1 over minus j is nothing but plus j. So that 1 divided by j into xc is nothing but 2 pi f into c. So that Xc is nothing but 1 divided by 2 pi f into C. So you can get capacitive current as J into omega C into VR. Once you get that from the phasor diagram, just look at here the phasor diagram. Is is nothing but IR plus IC. By adding IR and IC, you can get Is. By adding this IR and IC, you can get the value of Is. So Is is nothing but addition of IR plus IC. So substitute the value of IR and IC here. IR is nothing but IR into the bracket cos phi r minus J sin phi r, and IC just now we discussed, that is J2 pi f C into VR. So that you can get IS is nothing but IR plus IC from phasor diagram. Substitute the values, you can get this. So the voltage drop in each phase is given by IS into Z is nothing but a voltage drop of load per phase will be representing a one phase, so that IS into Z. If it is a two phase, 2 into IS into Z. So that Z is nothing but R plus JXL. Sending end voltage is given by VR plus ZS from the circuit diagram. So once you get Vs, then calculate Vs minus VR divided by VR. So how we are getting VR here? VR is nothing but the receiving end power, and Vs is nothing but, sorry, receiving end voltage, and Vs is nothing but sending end voltage. Once you get that, to find the efficiency, output power divided by input power. Here the output power is nothing but receiving end power, input power is nothing but sending end power. So that receiving end power divided by sending end power. So in a denominator, you can representing sending end voltage in terms of receiving end voltage, so that the power delivered per phase divided by power sent per phase plus total losses. Substitute the values of that, we can get the transmission efficiency as it is. So coming to the disadvantages, so this method assumes capacitance to be lumped, that is capacitance to be placed near the load, that is near the receiving end, although in actual practice it is distributed along its length due to its 10% error in calculations. And there is a considerable error, that is a 10% in calculations, because the distributed capacitance has been assumed to be concentrated or else lumped. So this method overestimates the effects of line capacitance is one more disadvantage. The nominal P method and nominal pi method we'll discuss in next session. Thank you.